Hello and welcome. The last differentiation under the integral sign, I promise. This is actually quite hard. It's not actually hard, it's probably long. And I only came across it the other day, so I couldn't resist it. So I thought, okay, let me make a video on this particular one. Okay, it's the integral from naught to infinity of the arc cot of 2x multiplying the arc cot of 4x. Quite clearly symmetrical. And we're going to do it by introducing two parameters. You got to excuse me today, I got a bit of a cough and my hands have a little bit of the shakes today, so I might be writing a little bit bizarrely. So when I introduce parameters a and b to replace the 2 and the 4 there, it's symmetrical, so it doesn't really matter. So a and b, I don't have space to write it here, but I'm saying they're going to be positive numbers and they are distinct. They're not the same number in this particular case. Actually, it will work, I guess, even if it is the same number at the very end. I never really thought about it. So, not to infinity, arc cot of 2x, and then we got, not 2x, sorry. I'm already going absent-minded. Not a good start. Oops, arc cot with 3 c's. What's going on today? The arc cot of bx dx, and we're going to do two differentiations under the integral sign. So let's first of all differentiate di by dA. I'm not going to be writing it in there and then moving it. We've done enough of this now, which should be quite good. So I'm going to differentiate, of course, that with respect to a. That's going to stay in there. I'm going to do that side workings there because we need to be very careful with this. D is with respect to a, and we're differentiating the arc cot of ax. And because I'm not keen on arc cots, let's call it, let's move into arctans. There's two ways we can write an arc cot to an arctan. For this one, the best thing to do is to say that's the same as the arctan of 1 over ax. And I'm going to be careful. Now, arctan differentiates to 1 over 1 plus this squared. So it's going to be 1 over a squared x squared times the differential of that with respect to a. So x is a constant, so it's going to be 1 over x times a minus 1 over a squared. So we're going to be a bit tidy. Pardon me, I did warn you. A squared x squared, multiply top and bottom of this fraction by a squared x squared. So it's going to look like this, and that's going to be a minus 1 over a squared x. What does it simplify now? All of this, we're going to lose the a squareds, and we're going to get a minus x over x squared, a squared x squared plus 1. So I think that is correct. So returning to the integral that we're doing, not to infinity, minus x over a squared x squared plus 1, and we still have the arc cot of bx. And of course, on the next line, we're going to take now differential with respect to b, dA by dB. And of course, I'm not going to write it down. It's going to be symmetrical. It hardly matters whether it was a or b, so it's going to be exactly the same thing with the a squared replaced for b squared. So let's write it here. A squared x squared plus 1 times a minus x b squared x squared plus 1 dx. I forgot the dx actually there. This is the bx of the argument of the arc cot, really. And finally, we have dA by dB. We need a lot of space. As I said, this one, it is actually quite difficult, but it becomes difficult because it's very long, very easy to make mistakes. And And this does not look pretty, does it? A squared x squared plus 1 multiplying b squared x squared plus 1 dx. Okay, let's make some room. And now we're going to need to somehow do this particular integration. What does it look like? It looks like we've got some kind of partial fractions in there. And this is irreducible denominators, but it's not actually, if you think about it, just I'm very tired at the moment, I want to do full workings. It's actually linear as such. If you make a little substitution, x squared is equal to big X, for example. These are just linear denominators. So this particular one will split. I'm doing the partial fractions. I'm not doing the integral now, just yet. So x squared over these two brackets, which I'm not going to write, dot, 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 blah, 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 is equal to some constant, let's say capital A, over, this is not a function of like ax plus b, it's just a constant, plus a b, bx squared plus 1. So I'm going to do it by equating coefficients. Really, it's probably easier rather than doing cover-ups here. So that's going to be identical to capital A, b squared x squared plus 1, plus capital B, a squared x squared plus 1. So the x squared will be identical to ab squared from this bit here plus a b little a, lots of x squared, and the constants is going to be a plus b. So evidently, by comparing sides, the a plus b must be 1. So that means from this bit here, we're clearly having that a is equal to minus b, or b is equal to minus a. It's the same thing, really. And that means ab squared plus ba squared, this bit here, is going to be equal to 1. If we, let's say, replace the b for minus a, we'll have ab squared, so I'm doing this bit here, minus capital A squared is equal to 1. Factorize your big A. So we found that the A is 1 over b squared minus a squared, and the b is the negative of that. I could have swapped it, but I prefer to have the same thing because I almost certainly will, I will factorize it out. So what do we have so far? I think we can just do another line here, dA by dB, and not to infinity. And we have, actually, I'm going to just, I'm going to factorize it on this line. So the a and the b, basically, they're here. So this quantity can be pulled out. So I'm going to write it outside the integral. So we have, hope you're following what I'm doing. These days I'm not, oh God, I'm not as good in explaining as I used to be. I'm very tired due to medication that I'm taking, unfortunately. So that's the common factor. That's now the a, which is going to be 1 over a squared x squared plus 1, and we have a minus 1 over. We have some luck here because there are a lot of symmetrical and identical, almost, or analogous, perhaps the right term to use, expressions. So we don't really need to do the work twice as such. So far so good. Oh, I moved my little pad here. Just bear with me. I just want to just make sure it's aligned in the right place and everything is in view. Okay. How do we integrate now? These are arctans. So I'm going to continue on the right hand side, but they're not quite arctans yet. So second derivative with respect to a and b is 1 over b squared minus a squared, not to infinity. In order to get it to the arctan form, I forgot the limits there, 0 to infinity, I need to pull out a 1 over a squared, that's from this bit here, I'm going to use a dot for multiplication, and I'm going to have x squared plus 1 over a squared. So that's just basically this bit here. I'm just putting it into the standard arctan form. This is done in further maths, not anything university maths or anything like that. 1 over b squared, symmetrical again, and it's going to be 1 over x squared plus 1 over b all squared dx equal 1 over b squared minus a squared. So I begin my integrations now. That's the 1 over a squared already there, and this is now the arctan produces a 1 over this, and then we got arctan of of x, I beg your pardon, 1 over a. That's the argument of the arctan, and symmetrically again 1 over b squared. This arctan will go 1 over b, and we have the arctan of x over 1 over b. Let's do a little bit of a tidy before we put any limits. Let's see what we get. This is going to give us a 1 over a arctan of ax and 1 over b the arctan of bx. Integrated, limits 0 to infinity. All right. What happens now? We have putting our limits in. Arctan of infinity is pi over 2. So that's going to give us a pi over 2a minus arctan of bx, exactly the same thing, pi over 2 as it goes to infinity. So that's the top limit. The zeros, I shouldn't really be writing anything really. Quite stupid of me, doesn't matter now. I put a bracket within a bracket. Hope you forgive me. What we can do there, we can just tidy this up. We can pull out a factor of pi over 2. So we have a b squared minus a squared, and inside that bracket we go 1 over a. This will simplify because we're going to get from the difference of squares. We said a and b are distinct. I wasn't quite sure if they have to be distinct for this to work, and it appears it does, because we have a problem if b is the same as a, then this is not finite. So a and b are different numbers. So tidy still to b minus a, just doing the difference of squares, b plus a, so that's this bit here, and tidying this up, b minus a over ab, cancel, and what do we have in here? We have pi on the top over 2ab, a plus b. Okay, doesn't look pretty, does it? Okay, so now what we need to do is we need to reverse our integrations. So what I'm going to do at this stage, because I need to create space, I will leave this for the time being just in case I need it. Let me just write all of this and just say, well, this quantity, remember that's all of that simplified to pi over 2a b a plus b. So we can remove all these workings on the right. I hope you're with me, and I hope you haven't fallen asleep or pulling your hair, because I don't think we're even halfway. I think we're probably quarter of the way, but actually not possibly a third of the way into this integral. It's messy. And when I say messy, not Lionel Messi, just messy. All right. So we have so far got this quantity. And what I'm doing, depending which integration I might choose to do first, I might do the one with respect to b first. So pi over 2. In this particular case, the A will be a constant, just looking at this, and times, what do we have there? We have 1 over, both A's, so you make mistakes, so it's just that. Okay, so I'm going to integrate int with respect to b first. So the a's are constants. I got partial fractions there, so this I'm not integrating just yet. This I'm going to do by cover up. So what do we have in there? We have, let's put a bracket when it's in b that I'm doing it. So when b is equal to 0, so b is equal to 0, we got a 1 over a over b. You can do your partial fraction whichever way you want. And when b is minus a, we have a minus 1 over a. That's the coefficient. And then we got a plus b. It's not too bad. So what do we have there? We can pull another 1 over a outside. I have to be careful. Let's go at the bottom, 1 over a. Yeah, it'll be pi over. Very easy to cancel this if you're not careful, and then it goes complete pear-shaped. And then we got a 1 over b minus 1 over a plus b. And I did say I'm going to integrate that now, going back one integration with respect to b. So what I'm left now is di by dA. The b is going, so this is a constant, pi over 2a squared, and these are just logs really, aren't they? So we got the log of b, because I did say the b are distinct and positive, I'm not putting moduli there, minus the log of a plus b. Put a bracket there. And what happens in this particular one, plus of course a constant from the integration. Probably from the limiting process, it's better to compact the logs there. Pi over 2a squared log b over a plus b plus c. So for this particular one, in order to find the constant, what do? We let a suitable value of b, and I think for this particular one, possibly infinity will do, to find what is di by dA. So if we look at what we got in here, I can possibly just about squeeze it. I'm just copying this line, that's my di by dA, all of this, so we can physically see it. I could actually just say, oh, look at this, and that's the same as that. I prefer to do workings, and I advise you, if you follow this lecture, to slow it down, pause it, and make sure you can see where bits are coming from. I'm trying to put reasonable detail, although we have done tons of this, because this is a bit messy, as I mentioned. So this is what we found so far, and I think, yeah, b tends to infinity, we'll do it for a fixed a. For a fixed a, and we go b over a plus b plus c. So if we put b goes to infinity, that's irrelevant. The r cot of infinity is in fact 0. So basically we'll be having the integral from 0 to infinity of 0. I did put dx there, do forgive me, on the integral. 0 dx is equal to pi over 2a squared. A is fixed. But now if b goes to infinity, that essentially will limit to 1. And of course the log of 1 is 0. This is 0. C is 0. Fantastic. So what we have found so far, just make sure we got all the bits ready. Let's rub off, make room. Is this line here, which I need to copy again. The C is 0. So I'm going to move it to the top of the tablet here. So it's basically that, but I want to make use of the space. So di by dA is what was it? Shall I leave it as separate or as compact? I think, oh my God, we have the integration by parts next. I think I need to have it separate really. Pi, the logs I'm referring to, so let's have it compactly like this, but no way. Pi over 2 a squared log b, and then minus the log of a plus b. So this is where we have got so far with this particular integral. And while I'm rubbing off, can you see the integration by parts? Because our next integration with respect to a. So this is not something on the outside, it needs to go in. So I need to rewrite it. So I'm going to leave just a pi over 2 on the outside from that. And this is not a problem. This one that I'm copying now, this is not integration by parts. It's just the a integration, it's just a constant. This is now the beast. So we got minus 1 over a squared, and then we got the log of a plus b. And this is now an integration by parts. So I'm going to do my little grid here. Whichever way you do your integration by parts, this is a little bit messy. I'm going to treat this minus so I don't forget it. So I don't have to do minus and then get my things. I'm going to treat it as being part of the minus 1 over a squared. So I'm going to differentiate the log of a plus b. My integration, remember now, is with respect to a. So not that it matters here. Is 1 over a plus b. There's no change. So I differentiated this bit here. And I'm going to integrate the minus 1 over a squared, which is with respect to a. So that will go back to 1 over a. So pi over 2. This is not integration by parts. This is just basically a constant and integrating that. So it's going to be minus 1 over a log b, this item. The minus I've taken care of, so that is equal to, that's the parts now that I've done in there. The product of this column, which is 1 over a log a plus b, minus the integral of this diagonal. And this diagonal is, of course, a, I'm writing stupid things, a at the bottom, no more partial fractions, please. And what's the, with respect to, we're integrating back into a, so that's dA. Yeah, small partial fractions. All right. There's no limits here. We're going to get a new constant, call it d. So let's tidy still. This is not now, this is now our I, because we integrated backwards, the I of AB. I'll put the AB here because I didn't leave enough space on this slide to do it. So the timesing a few bits out here. And so actually I probably won't, because I still got to do partial fractions there. This I will do by cover up. Be careful the an A does not become into B very easy. My handwriting, as I said, I'm shaking. I'm not writing very well. I don't know for how long I'll be able to still do this kind of thing now. All right. Is with respect to A. So A is 0. So this time is 1 over B over A. And the other one, when A is equal to minus B, is minus 1 over B. Let's put it at the front. And this is now A plus B. dA. Close bracket. Okay, let's hope it all works out good. So this is equal to pi over 2. Loads of copying. That's for mathematics. As you might be just wondering, what's the point of all of this? It's an exercise in concentration. That's what it is. I mean, anybody who can do that should be very, very proud and say, look, I'm very special. I can still keep track of things. I'm like a brain surgeon. That's how I see myself sometimes. Okay, this is stupid perhaps. And these are logs, okay, with respect to A. So I'm just going to do the integration, put the constants at the same time. So minus 1 over B, that's this bit here, log of A, minus minus is going to go plus, still 1 over b, and the integration is of course with respect to a, it hardly matters, it's linear, so it's log a plus b. And of course we got plus d there. All right, what can we do now with this particular one? We really need to evaluate this d, so we need to put this quantities a little bit better, otherwise we will just lose the plot here. So leave the pi over 2 on the outside, and let's put these two bits together. So 1 over a factorized, so we're going to have log of a plus b over b, and if we factorize the 1 over b log that over that, again a plus b, but this one is over a, just checking, a plus b over a plus d. All right, so far so good. So what do we do this time? The last time we let b goes to infinity. This is symmetrical, so almost certainly I'll change it if it's not the case. A goes to positive infinities for some fixed b in order to work out my constant d. So what is my I? Remember, this is now I of a and b, and I of a b is in fact the r cot of, let me just write it, the I of a b, it's up here, is not to infinity arc cot ax r cot, probably fits, dx, and it's equal to, oh, I don't think I'll be able to fit all of this, so I'm not writing it, is equal to that, all of this quantity, including the constant at the end. So I'm letting a go to infinity. If a goes to infinity, we have r cot of infinity, so this particular thing will be 0. 0 dx from this limit is 0. So what happens now as a goes to infinity? First of all, this is easy to see. B is fixed. This will be log of 1 as a gets massively large, the ratio approaches 1. So this is 0 plus d. The question is what happens to this one, because of course we have a going to infinity. So what's log infinity? Well, it's of course not finite, but it's not log infinity as such. I have no space and I don't want to write it. I'm going to use a different color pen, and I hope it shows good in the video. I'm going to do it in red here. I got a bit of space here just so we can see. We try to limit this quantity here. So that's 1 over a log, I'll let you see because probably my hand's in the way at the moment, over this. So this is the quantity here, and a goes to positive infinity. Well, if you let a goes to positive infinity, this quantity goes to 0 faster than this quantity going to infinity. So it's dead. Okay, so in fact the d will be 0 as well. So I hope you follow this one. It's a little bit busy in the board with the parts and everything else. So far, where are we? What have we actually found so far? It's basically this line here that we've got, which I'm going to leave it so I can see it, but d is 0, so that's not there really. And I think now we might be home and dry, I hope. I think it's putting stuff in. We're nearly done. Let's leave it in there and let's clear the board. I hope you still enjoyed it. I hope you haven't fallen asleep, and I hope none of you is pulling the hair. Oops, I moved the thing. Just give me a second just to realign my board again so we can all see what I'm doing. Oh, come on. Moved again. All right. This video is going to be a little bit long. I do apologize. Just double checking again the tablet. It's running almost 30 minutes at the moment, so We just took our time, I guess. So far, this is let's write it. I'm not going to write it again. It's all good. Just lose the bits from the other side. From underneath rather, so on the other side. Okay, so finally, our I, which is this is what we're trying to find, of 2, 4, A2, B is equal to 4. Okay, what does it produce? It gives us the following quantity is equal to pi over 2. Looking at this, 1 over a, so that's going to be a half log 6 over, oh come on, I'll change the next line, a half log 6 over 4, 1 over b, which is a quarter, again log of a plus b. Let's leave it like I had on this, 6 over 2, there's nothing that did, of course it was 0. So basically the integral from 0 to infinity, because that's of course the I of 2, 4. Let's write it. We spent all this time dealing with him, so might as well just put the extra line to make it extra pretty. Dx is equal to pi over 2, a half log of 3 over 2 plus a quarter log 3. Can we tidy this up a little bit more? Pull out a quarter, so we're going to get pi over 8. That's going to give us 2 log of 3 over 2. From this one, the quarter has gone, plus the log of 3, which is equal to pi over 8 log of 9 quarters plus the log of 3. And I hope I've done it correctly. I can't remember the numbers as pi's, logs, and there was a 27. I don't quite remember the exact answer, but I think it looks about right. Log 27, I remember. I could be, I hope I'm not wrong with this particular 4s and 8s, and I've done something stupid or something like that. And therefore, that's my final answer. And actually didn't take as long as I thought it was going to take. And I hope you enjoyed it. I hope you followed it. And I promise, unless I come with something so unusual, this, I think, in the playlist will be the last differentiation under the integral sign. I'm signing out. I will see you real soon.